So we reviewed the material from yesterday where we were graphing sinusoidal functions, which includes cosine. Cosine is a sinusoidal function. Let's then take up in the text from there. Yeah, that's the next section. So I want to go back to the exercises from this section. And we had just done 41, right? Okay, so that's up here, right? And so there's, 42, 40, 42, yeah, 42, 43, 44, 45, 46. Those are all sort of the same kind of animal, right? Some transformation of your basic trig functions, sine and cosine. So 42, let's do 44. Well, let's do 43 and then 44. Okay, why not, right? So I'm just going to copy over to my paper. So this is 5.3, number 43. And what do we got? Okay, I'm just going to read it off here. So y equals 3 times the cosine of pi times a half more than x. Okay. And again, the instructions are, I don't know, shall I read the instructions? Find the amplitude period and horizontal shift of the function, then graph one complete period. I think you should also find the vertical shift, right? This one doesn't have a vertical shift, but the last one did, right? You shifted up one. This one is just going to oscillate. Let's around 0, right? Around the x-axis. So the amplitude equals 3. That's this number here. And the period or wavelength is equal to 2 pi over pi, which in this case is going to be 2. And the horizontal shift, I'm going to abbreviate horizontal if you don't mind, is -1/2, right? To the left. Okay, so make a table of values. Start at the horizontal shift, right? Because that'll give us our 0 for cosine. So when x is -1/2, what is y? Well, it's going to be -1/2 plus a half is 0. Pi times 0 is 0. Cosine of 0 is 1. And 3 times 1 is 3. So then what's a quarter wavelength? Maybe I should say, so a quarter period, if you like, is 1/2. That's convenient, right? Oh, sorry, that's off screen. So it's 2 divided by 4, right? A quarter of 2 is a half. 2/4 is 1/2. And so I'm going to do increments of 1/2 here. So 0, 1/2, 1, 3/2. And that'll take me through one complete wavelength. Yeah. And so we're going to be back to equilibrium at the trough, back to equilibrium, and then back to where we started at a peak, right? Because it's a cosine function. And so when we make the graph, we will, oh, look, I've got my I voted sticker. That makes me virtuous. I'm virtue signaling. I don't know how that got there. Okay. Okay, so I'm going to make a quarter wavelength equal to an inch. 1, 2, 3, 4 quarters. Oh, let me mark those positions, right? 1, 2, 3, 4, 5 hash marks gives me 4 subintervals, right? And I'll put the y-axis at the second one, since we're actually, the phase shift is a quarter wavelength to the left, right? Don't forget to label your axes. And we're going to start at a peak because it's a cosine function, right? So this is -1/2. This is +1/2, 1 and 3/2. Those are the corresponding inputs in my table. And let's say the peak here is at 3. Equilibrium, -3. I want that to be perfectly evenly spaced. Okay. I guess about there then. -3. So here's my trough, equilibrium, and back to peak. And then, you know, practice making a good sinusoid shape through those points. And it's going to look something like that. And of course, it continues on, both to the left and to the right. Yeah. But we captured one complete cycle of this function, and that will allow us to just replicate that over and over ad infinitum. Okay, so 44. So this one, you know, let me just say that this one turned out to be very convenient, right? Leonardo, I gotcha. Okay. So why is it convenient? Well, because the phase shift was a quarter wavelength, so you're really not out of sync. In fact, you could think of this as a sine curve. You see that? You know, a negative sine curve, right? So it's a reflection through the y-axis of a curve that would go from 0 to 2, right? And so we could say, yeah, another way to write this function is negative sine of pi x, right? Without a phase shift so much as a reflection, right? So it's an inverted sine wave. Yeah. So, you know, every cosine curve can be written in terms of sine. You just shift or reflect or some combination thereof, right? Okay, let's look at number 44, I think would be next. Yeah, that's the number after 43 on a Wednesday. So here's number 44. And the function formula is y equals 3 plus 2 times the sine of 3 times 1 more than x. Okay, so what's our amplitude? That's 2, right? Okay, so the amplitude here is 2. The vertical shift, should we write that? Let's say the vertical shift equals shift equals 3. So so what are we going to oscillate between? Well, 2 less than 3 is 1, and 2 more than 3 is 5. So we're going to be oscillating between 1 and 5. The y value will be oscillating between 1 and 5. And what's the period of oscillation? Well, 2 pi over 3, right? Just look at this number here. That's what's multiplying the input. So 2 pi over 3. And the phase shift, or the horizontal shift, is -1, 1 to the left, right? So how about a quarter wavelength, as long as we're at it, right? So a quarter wavelength. And why, you know, your book doesn't emphasize this, but I think it's a darn handy thing, right? That's where so the period is 2 pi over 3. Now, that's going to be a little bit more than 2. All right, so maybe we should approximate. So why am I approximating? I didn't approximate that before. Let's see, pi over 3 is approximately, so why am I doing that? Well, it's because the phase shift is not a multiple of pi, right? See up here, the period was not a multiple of pi and the phase shift was not a multiple of pi. So you just had rational numbers for both the period and the phase shift. Here, the period is a multiple of pi, or, you know, a rational number times pi, but the phase shift is not. So that's kind of put you off, right? So you want to kind of resolve those. So pi over 3, well, 3.14 divided by 3 is 1.04, closer to 1.05 maybe. So twice that is 2.0. Sorry, 2.1 maybe. So this is about 2.1. I'll use a calculator maybe to verify that. Do we have a calculator? Where's my calculator? Verify this. I think did I put it here in shortcuts? Yes, I did. And where's the executable? There it is. And I want, okay, so let's see if I choose to view that. I think I can do that. Is it not? I thought we had a tab for that. Is it just window capture? Doesn't seem to be anything there. Let me say properties for that. Okay, so there it is. And let's see. Okay, do I want to change the name of this thing? I suppose so. Just rename this. Okay, so this is TI Calc. Okay, and you can see it there. I think it's visible on the screen, is it not? Yeah. And it's kind of a cheesy little calc. So maybe I want to pick a different one. Sit calculator ROM version. I kind of like the 85. Got a soft spot for the 85. Oh, it's not changing. Okay, there it is. All right. Accidentally clicked on the, didn't mean to do that. I wanted to make my graphing calculator larger. So you got to turn it on and you can hit the clear button and maybe exit to get out of those menus. And then we want to say pi. Where's pi? It looks like I'm a little bit, yeah, I'm more in sync than. Remember the last time we were kind of out of sync, but now you can see my arrow is in the right place. So I hit second. I'm looking for pi. It's over here, right? And then divided by 3. Yeah, pretty close to 1.05, right? So then if I multiply that by 2, I get something pretty close to 2.1. So that's why I wrote that on my paper here, approximately 2.1. So a quarter wavelength is going to be 2.1 divided by 4, approximately, right? Which is 0.05. Let's see, 3. Can we say that? Rounding off, something like that, right? Okay, so let's make a table of values, right? So this is the rule of three at work here, right? You've seen the rule of three at work? What are the three? Well, you've got numerical values, you've got geometric interpretation in the form of a graph, and the analytical or algebraic formula, right? Trigonometric formula, perhaps be a better way of saying that. But yeah, so those three things, the rule of three. So here we have our trigonometric formula, and I want to tabulate numerical values for input and output. So if the input is, well, let's see, what's the phase shift? -1. So if x is -1, and this is sine of 3 times 0, which is sine of 0, which is 0, and 2 times 0 is 0. That's a lot of zeros. But 3 more than 0 is 3. So we're up here at 3, right? And let me put this aside here. Okay. And so then I want to go a quarter wavelength. So, you know, I could add, what is it? Pi over 6 would be a quarter wavelength, 2 pi. So pi over 6 turns out to be pretty close to 0.53. Right? Should we verify that? So here's second pi divided by 6. Actually closer to 0.52, huh? Yeah, a little bit of a rounding error. Okay, so maybe I'll change that here then. This is actually closer to, see, I rounded up the 2.1 and I rounded up the 0.025, and so I got more than I should have, right? So it's actually closer to 0.52. Okay, so now do we want to put approximate values in this table or exact values in the table? Well, we're going to make a graph, right? So we probably want approximate values. Let's put both in, okay? So I'm going to say my starting value -1 plus a quarter wavelength, which is pi over 6, so -1 plus pi over 6, and that's approximately -1 plus 0.52, which is going to be -0.48, where we'll be at equilibrium. Oh, sorry, will be where this is a sine curve, right? So we're going to be at a peak. So that's 3 plus 2 is 5. All right, and then 2 quarter wavelengths is going to be pi over 3. So -1 plus pi over 3. That's approximately, we said pi over 3 is about 1.05. So this is going to be approximately 0. Sorry, 0.05. Huh? Yeah. Rounding is a little bit tricky here, isn't it? Okay, so let me see if I can fit it out. 0.05. Is that legible there? Barely, huh? In which case we'll be back at equilibrium. We went up to the peak and then coming back to the equilibrium. So now 3 pi over 6 is pi over 2. So -1 plus pi over 2 is our next input. And then we're going to add 0.52 to 0.05 to get 0.57. Which will be at the trough, which is 2 below equilibrium. And then if we add an entire wavelength of 2 pi over 3 to -1, 2 pi over 3, that's going to be another 0.52. So I'm going to say that's 1.09 approximately. Should we check that maybe? Because you get a little rounding error, right? So if I go back to my calculator and I say, tell me, oh, great calculator. If I have 1 and I change the sign of 1, is that here? Oh, no, that's, so I need to go back here. So I'm going to say -1 like that. Whoops. Let's clear that. -1 is what I want here. Plus one wavelength is 2 pi, 2 times pi divided by 3. I get 1.09 approximately, to the nearest hundredth, which maybe I should round to the nearest tenth. I don't know. But that's then one complete oscillation. So we're back at equilibrium, which is going to be 3. All right, so now that I have my numerical data, it'll be easy to make a graph. Right, and so where's the action? Well, the y values are all between 1 and 5, right? So I'm going to put my x-axis down low. It's on the down low. And I'm going to say, yeah, an inch is a quarter wavelength again. So maybe here, here. So that's 2 quarters, 3 quarters, 4 quarters is a whole. Oh, 4 quarters, that's here. My hash marks were not going to be perfectly evenly spaced. And we're starting again about a quarter wavelength. Oh, about half a wavelength, huh? To the left. Yeah, we're starting at -1 and the wavelength is approximately 2.1, right? So let's put the y-axis here. And we'll say a half an inch is a unit on the y-axis. So I think that'll count 1, 2, 3, 4. Oh, that won't quite do. How about 4, whatever these are? 1, 2, 3, 4. That's still not going to do it, huh? I want to be between 1 and 5, right? That's unfortunate. Okay, well, fortunately, we have erasers. Unfortunately, it didn't plan very well. Okay, so let's make, what are these, 16ths, I think? Okay, so 3/16 of 1, 2. Oh, well, how about 2/16? Okay, so 1, 2, 3, 4, 5, and there's 6 for good measure. Okay, perfectly evenly spaced, right? And that's, I'm going to label the y-axis and x-axis, and I'm going to say here is my phase shift is -1, so this is 0. Oh, sorry, that's -1/2. Good thing for this eraser, right? I'm not using that Sharpie anymore. And so this is +1/2 and 1. And that will give us one complete wavelength. So let's sketch in the line of equilibrium, which is 2, 3. Okay, I'm going to make it a dashed line here, like this. And so we're starting here at equilibrium, -1, 3, right? Then we're up at a peak at -0.048, which is just a hair to the right of, you see why we had to go to decimals here, right? Because, and then 0.05 is just a hair to the right of the y-axis. And then 0.57 is just a hair to the right of there, a hair from there, said the tortoise, who taught us all about it. 1.09 is then, a tenth of an inch to the right of, 1, so about there. Oh, is this, okay. So there are the 5 guide points for my sine curve. I'm going to try to make a nice smooth sine curve through those points. And something that looks like that, right? And of course it continues on, right? All right, so that was a little harder because we had to resolve the difference between, multiples of pi or, fractions of pi with decimal values, since the phase shift is not a multiple of pi. So when that happens, you just got some extra computations to figure. Use a calculator, I guess, right? I did. Questions about all of that? Can something about the camera here? Move the camera. Oh, yeah. Yeah, I have to remember to keep monitoring. Yeah, okay. So I think that captures most of that. Maybe I'll kind of make me smaller there. It's mini me. Oh, I'm disappearing into the corner. Whoop. But yeah, so there, there's all that information. Okay. All right. I don't know. More of these? That was kind of tough. How about 45? There we've got pi plus 3x as the input to a sine function. And if we factor out the 3, we'll have a wavelength of 2 pi over 3 and a phase shift of negative pi over 3. And so those are consistent. So that would be easier. And 46 is pretty straightforward too. Okay, so I'm going to go to 47 through 54. They want us to go the other way. So yeah, I've been mentioning this rule of 3. You got your trigonometric formula, you've got your numeric data, you've got your geometric interpretation in the form of a graph in the Cartesian coordinate plane. So what if you were to first start with the data or first start with the graph? Could you get the formula from the data or the graph? And I would say yes, depending on, if the data were in the form of the 5 points of, equilibrium peak, equilibrium trough, equilibrium, then that would tell you what the wavelength is, and it would tell you what the amplitude is, and what the line of equilibrium is, and the period, right? So from that, you could construct your trigonometric formula, right? So let's go to the book and see. Yeah, they've got some graphs. We would like to then say, what is a formula for this graph, right? So I'm going to go to 47. Let's do 47. So I will reproduce that graph on my paper, and then from that make a table of values and find a formula. So here's number 47. Given the graph, find a formula for the function. All right. Let's go to this pencil. So do we have to make a nice graph? Yes. How do you do that? I don't know. So here's so we've got one complete waveform, and it looks like it's a sine waveform. So I'm going to say 1/2 inch is a quarter wavelength, and label this as the x-axis. And they say that this is 2 pi here, and this is 4 units up and 4 units down. So let me extend this down and say 1/4 inch is a unit. And so here's 4 1/4 inch lengths. This is the y-axis. This is 4, and here's 4 down. That's -4. And we're starting at equilibrium at a 1/4 wavelength, which is going to be, so here's pi, right? Halfway to pi, 2 pi. So here's pi over 2, and this is then 3 pi over 2. And we're starting at equilibrium, going up to a peak at pi over 2, the equilibrium at pi, a trough at 3 pi over 2, and then back to equilibrium. So our trig function looks kind of like that. Never mind this errant bit. Whoops. Okay, so it's kind of like that. All right. Um, so what's the amplitude? Well, it's 4, right? Because we're going up 4 and down 4 from equilibrium. What's the wavelength or the period? That's 2 pi, which is equal to 2 pi over b. And so that implies that b is equal to 1, right? What's the phase shift? It's 0, right? It's not shifted at all. Um, so when you go back to our um, generalized formula, right? We now know A is 4, D is 0, we're oscillating on 0, B is 1, and C is 0, right? So this is simply y equals 4 times the sine of x. Was that obvious enough? Maybe I overdid it, right? But you want to sort of, when it's not so obvious, those are the steps you go through. Could we also write that as a cosine? Sure. What would you say? Well, the cosine, you'd shift to the right, pi over 2, right? So we could say this is 4 times the cosine of x minus pi over 2. That would be also a perfectly good answer here, right? Find a trigonometric formula. Well, that works, right? Absolutely fits the curve. Or, if you want, can we even do something else? Yeah, I think you could say negative sine of x minus pi, right? Since if you were to shift to the opposite side of the unit circle, then you'd have the opposite. Okay. I think probably the simplest one is the best, right? 4 sine x. Okay, you have another one of these? You bet. We've got a million of them. So 54, huh? So how about 52? Or 51? 51 looks challenging enough. So here is 5.3, number 51. And I'm not going to be so fussy about my graph. I'm just going to try to capture the essence of what's going on. Negative pi over 3 is the starting point, and 2 pi over 3 is the ending point. So here's negative pi over 3, perfectly evenly spaced hash marks. So each one is pi over 3. So this last one is 2 pi over 3. And we start at a trough. Halfway between these is going to be where? Well, that would be the average of these two numbers. If you add up negative, right, the midpoint of a segment is the average of the left and right endpoints. So if I add these up, I get pi over 3. Half of that is pi over 6. So this is pi over 3. Halfway from 0 to pi over 3 is pi over 6. And that is going to be the peak. So the trough is at negative 1/2. And so the peak is at positive 1/2 up here. It's oscillating around 0. So we start here and we end there, right? At, the same y value, right? The peak is here. And where's equilibrium then? I mean, where do we cross the equilibrium? Which is the equilibrium is going to be the x-axis. So that's going to be the midpoint of the interval from negative pi over 3 to pi over 6. Negative pi over 3 is negative 2 pi over 3. So I'll write that out here. So negative pi over 3 plus pi over 6 over 2 is the computation I want to do in order to find where it's going to be at equilibrium. Halfway from negative pi over 3 to where the trough is to where the peak is at pi over 6. And I don't know, You could multiply the top and the bottom by 6. You get negative 2 pi plus pi over 12. That's one way to do that. So that's pi over 12. Okay, yeah, sure, pi over 12. Oh, negative pi over 12, right? Yeah. So here's negative pi over 6. So negative pi over 12 is going to be halfway in between there, right? Shall we be working on the table of values while we're at this? Okay, so x and y. We know x starts when the curve starts when x is negative pi over 3. We're at negative 1/2. And at 2 pi over 3, we're also at negative 1/2, right? Halfway in between, pi over 6, we're at the peak, which is 1/2. So where are these equilibrium points? Well, we found this one is negative pi over 12. Halfway from negative pi over 3 to pi over 6 is negative pi over 12. And that's right there, huh? And so then what's halfway from pi over 6 to 2 pi over 3? Now we could do the same sort of thing. I'd say pi over 6 plus 2 pi over 3 divided by 2. That's halfway between, right? And I could multiply the top and the bottom by 6 again. I get pi plus 12 pi. Sorry, 4 pi. 3 goes into 6 twice. 2 times 2 is 4 over 12. So that's 5 pi over 12. So that's going to be the other point where we're at equilibrium. And let's see, if I mark by pi over 12, so we got 1, 2, 3, 4, 5 pi over 12, right? So that's, pi over 3 is 4 pi over 12. And so 5 pi over 12 is one hash mark there to the right of that. And so here's my graph. Passing through these equilibria. So I've got, I don't have the formula yet, but no, do I? Right? I've just got these points. So what's the amplitude? That's 1/2, right? What's the wavelength or the period? That's 2 pi over 3 minus negative 2 pi. Sorry, I'm going to say 2 pi over 3. I'm going to do the computation here. Okay, so 2 pi over 3 minus the left endpoint. So it's a difference. You subtract the left endpoint from the right endpoint, you get the length of the interval. And so that's going to be pi, right? Which is equal to 2 pi over b. And that implies that b is equal to 2. So this is A, right? This is B. D is equal to 0. What's C? Well, C is our phase shift. So what kind of animal do you want to call this? You want to call this a sine or a cosine? Well, since we're starting at a trough, it's kind of a negative cosine. So you could go with that. And then your shift would be pi over 3 to the left. So you could write y equals the amplitude is 1/2, d is 0, right? So, oh, and then it's negative, right? Because we're starting at a trough. Cosine of b is 2, and the shift is pi over 3 to the left. That's fairly complicated looking. You got a negative multiplier. That's not nice. Let's interpret this as a sine function instead. So if it's a sine function, we're thinking, well, I'm starting at equilibrium, which is here. All right, so I got the same wavelength. I've got the same amplitude. What's different is the phase shift, right? And the phase shift, so we're at equilibrium when x is negative pi over 12, right? And so I would write this as positive 1/2 because we're starting at equilibrium and going up. Sine b is 2, x plus pi over 12, right? So that's a shift to the left of pi over 12. So those are exactly the same curve. So the graph of those two functions is exactly the same curve. Are they exactly the same function? Well, they look quite a bit different, right? So no, they're not exactly the same function, right? When x is 0 here, well, you're at the same point on the curve, right? So the xy pairs are all the same. Maybe it's an identity, right? For all values of x, this is equal to that. They look quite a bit different. I kind of prefer this one. In fact, I would prefer to say, if for the cosine function, I would prefer to start at a peak. And in that case, we'd have 1/2 cosine d is still 2. But now to get to the peak, we'd shift pi over 6 to the right. So all three of those will give you exactly the same curve, exactly the same xy pairs. The first one, I think, is the least preferable. I like the second one because it has the smallest phase shift. But notice that the phase shift, the size of the phase shift for this one is smaller than the size of the phase shift for that one. So it's got, this one has two things I like better about it than the first one. One is that the multiplier is a positive 1/2. Accentuate the positive, eliminate the negative, and don't mess with Mr. In between. So then it also has a smaller phase shift, right? Pi over 6 is 1/2 of pi over 3. And it's in the positive direction again, right? So our phase shift is to the right rather than to the left. Going to the left, that's a sinister phase shift. You don't want that. Did you know that sinister means to the left? We could go to our OED and look that up. Sinister. Given with intent to deceive or mislead. Yeah. Promise, practice. That's the first definition. Prejudicial, adverse, unfavorable, darkly suspicious. Well, that's terrible. Dishonest, not straightforward, underhanded, dark. Where's the corrupt, evil, bad, and base? Oh my goodness, this is looking bad. I'm not finding my definition either. Astray from the right path. Oh. Of persons acting or advising to one's detriment. Of omens portending or indicating misfortune and disaster. I'm not finding my definition. Here you go. Situated on the left side of the body. Sinister. I don't know. What? So for all you left-handed people, I'm sorry. This is like a bad connotation. It's wrong. Okay. But you know, hey, language is language. Definitions are definitions. Okay. So where does that take us? Well, I think maybe back to the book. Sumatra. Yeah. And there's more exercises. Hard to believe, but it's true. Determine an appropriate viewing rectangle for each function and use it to draw the graph. Oh. Well, for all of these, you know, you've got a value of b, which is going to determine the frequency of oscillation. And they've got a little graphing calculator next to it too, right? So let's do one of these. How about number 56 there? So you got the sine of 3 times the sine of 120x. So what would an appropriate viewing rectangle look like? Um, and let's go to pencil and paper for a second. So this is number 56. And here's the function, sorry. F of x equals 3 times the sine of 120x. So the amplitude is 3. The wavelength. Sometimes we use the character lambda for the wavelength. That's a Greek letter L for length, right? And that's equal to 2 pi over 120, or pi over 60. So what's the frequency? Well, 60 over pi, right? It's the reciprocal of that. That's the number of cycles per unit length. Okay. So let's make a quick table of values, shall we, based on just this information? There's no phase shift, right? So x and f of x. So we're going to start at 0, 0, right? Then a quarter wavelength is going to be pi over 240. So we say pi over 240. That'll take us to a peak, which is 3. 2 quarter wavelengths will be a half wavelength, which is pi over 120. And then we'll be back to equilibrium. 3 quarter wavelengths is going to be pi over 80. Right? So 1 quarter is pi over 240. I just multiply that by 3 to get 3 quarters. And then we'll be at the trough. And a whole wavelength will get us to pi over 60. And that's back to equilibrium, right? So, we can graph this easily then, right? Just 1, 2, 3, 4 quarter wavelengths to pi over 60. Started at so the y-axis, the x-axis. There's 3, negative 3, and peak equilibrium, trough equilibrium. Boom, there's my graph. Let's do this on the TI-85, right? No, that's the, okay. And I'm going to say, is that calculator is a little small, huh? I think, okay, if I do this and then, you won't see so well the buttons I'm pressing, right? But that's okay. I'm going to turn it on. I'm going to clear the screen. Whoop, clear. And I'm going to say y equals. And that button is somewhere. Sorry. Been a while since I used this calculator. I used to know it like the back of my hand, but there's so many different calculators out there. Is it like F1 or something? Quit mode, insert link, alpha, solver, simulpoly. There must be. How do you graph something on here? For goodness sakes. The keys are a little bit worn down, so you can't read them very well. Yeah. I'm drawing a complete blank. Maybe do I need to go into mode? Well, no, that isn't it. So exit that. Graph. Okay, so there's a graph button. Sorry. And so you get a y equals, right? And so I'm going to clear out what I've got there. All right, so y equals what? Well, what's our function? 3 times. Oh, not all the buttons. I think we don't have implicit multiplication. I forget even whether you have implicit multiplication. So I'm going to put times. Then I'm going to say sine, which is here. Oh, that's inverse sine. Um, oh, that doesn't work so well. Let's clear that and just do it again, right? So 3 times the sine in parentheses 120 times x. And if I hit the range button here, you can see I'm going from -2 to 2. Um, let's just go for the standard range, right? Um, is there a way of changing it to standard range? Um, no, okay. Well, let's just graph it here. Oh, graph y equals, so it's still there, right? And then I press enter or something, or, oh, I say exit and then F5 will graph, right? And what do we see? Well, kind of a mess, right? I think we're seeing some artifacts. So it's trying to oscillate 120 times per unit length, right? And we have 4 unit lengths going across here. So this should be 480 oscillations. It doesn't look like 480 oscillations. In fact, it looks like a mess, right? So what do? Well, we change our range to start from, oh, I hit exit instead of, so I hit the graph button, then I hit the range button. And I want to start from 0 and then go to one wavelength is going to be pi over 60, right? So I'm going to go to pi divided by 60. Okay, that's a very small decimal value. How about the x scale? I'm just going to use 1, I guess. The y min, well, that should be maybe -4. You know, it should include -3 and +3, right? So now if I hit the graph button, I see, yeah, one nice smooth oscillation of the sine curve. Yeah. Um, and that would be an appropriate viewing window. So when they ask you what's an appropriate viewing window, they mean what is X min, X max, Y min, and Y max that will capture a good oscillation, right? If I were to go from 0 to, let's try pi over 3. So that would be like, should be 120 oscillations approximately, right? So I'm going to say pi divided by 3. I'm going to see if we see this. Uh, yeah, is that 120 oscillations? Well, I don't know, count them. I'm going to say 5, 10, 15, 20, 25 oscillations, maybe somewhere on that scale, maybe 24. And so that's not nearly 120 oscillations, which it should be. So that's that aliasing. We talked about the aliasing effect when you sample at a rate which is not enough to capture the frequency, the actual frequency of oscillation. So what if I say like pi over 6 for the range? So from 0 to say pi over 6 and graph that. Then it looks like it's oscillating less, but smoother. So that should be 60 oscillations. Is that 60 oscillations? No. I think I can count them now though. 1, 2, oh, sorry. 1 peak to peak is an oscillation, right? Yeah. So 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 oscillations altogether. So yeah, pi over 6, which is 1/10 of pi over 60. I get 10 oscillations instead of 100 and, well, maybe that's actually right, huh? So if a wavelength is pi over 60, that's 1/10 of pi over 6. Oh yeah, okay. Actually, that's good then. So but just be careful when you're using technology to graph trig functions and you've got a high frequency trig function and a low frequency sampling rate. That can cause weird artifacts, aliasing effects. Okay, well, we didn't get to, yeah, I'm trying not to rush this stuff. I hope that's okay. Students usually prefer not to be rushed, so I suppose it is okay. But let's just take a quick gander maybe at what's next. All right, so what's next is, oh, let me turn off the calculator. Uh, there's some nice problems here at the end, but let's, the additive synthesis kind of problems, but more trigonometric graphs. So so far we've graphed sine and cosine, but what about tangent, secant, cosecant, and cotangent? Well, we want to look at those next, okay? So we'll take up with that tomorrow. You can see what those shapes look like. They have vertical asymptotes, right? Because you have the reciprocal functions. And so when the output of sine or cosine is 0, then the reciprocal is undefined or approaching infinity asymptotically. And so that's what we see with these other 4 trig functions. So these are secant and cosecant style functions, and the tangent and cotangent functions. No, it just froze up. Yeah, so these are like tangent functions here. This is tan 2x. And so you have the same issue of periodicity. Actually, the period of the tan function is only pi, not 2 pi. And we'll have to talk about that tomorrow. But we are out of time. Let me ask you if there are any questions before we adjourn. Okay. Go to the gallery view. All right. All right. Well, thanks for your persistence and attention, and stay. There's a new homework assignment there for you. And I'll bid you a pleasant afternoon and reappear in my office.